Good afternoon, everyone. So today I'll share with you some of the research directions that we are pursuing in my lab. As we all know, it's a very exciting era for AI these days. Right? I mean, we have algorithms which have achieved superhuman performance on these games. We have built computer vision systems which can segment images in great detail. Right? I mean, you can have systems which produce outputs like this, which seems almost too good to be true. And then we also have like an impressive suite of robots which are beginning to come about. But let's look at these systems in slightly more detail and how are we constructing them today. For example, if I want to teach a computer what is a zebra, the way I do it is I show many, many, many images of a zebra. So in a way, behind every success in computer vision, there lies a human farm. We are leveraging these humans to go and label all this data for us. Similarly, if you look at these domains of games, like the Atari games or the Go result which came out recently, computers actually require lots and lots of interactions, like millions and millions of interactions to actually play these games. And these successes have come out in the domain of games because it is possible to do so many interactions. I mean, imagine a robot trying to do something a million times or like hundreds of millions of times. That won't really be practical. And in these games, you already know the model of the world because you know what the rules are. Like in the real world, when you're interacting, you don't really know where the rules are, as Julie was talking about in the social context. It's unclear, right, what those things are. Then, if you look at systems like this, and this is an impressive feat of engineering that we can do this backflip. But the system is specialized for this one particular task, which is doing this particular backflip. Right? So in a way, if you look at AI systems that we have built today, these systems end up either working in simulation, they require a lot of supervision, or they end up being very specific to one particular task. And what we want to go towards are systems which can work in the real world, don't rely on so many assumptions or knowledge about what the rules of the world are, and can maybe do a bunch of different tasks. So the question is, how do we end up building such systems? So let's start with an example, right? So suppose I have a robot, and it sees this image of a table with a bunch of objects kept on it, right? And I give a separate image to a robot, which is showing a reconfiguration of these objects. And what I want my robot is to produce a sequence of actions so it can reconfigure objects shown on the left image to the configuration in the right image. Right? And the only inputs I'll give to my system are these two images. A related similar task could be where I show you an image of a rope in this configuration, and then I want the robot to go and tie a knot. And the way I'm communicating, I want the robot to tie a knot is by giving it an image which shows a knot. So let's look at how do we approach these problems today. So one approach is reinforcement learning. So in reinforcement learning, the goal is that given I have my state, say an image X, I want to come up with an action. Right? Now, this mapping between state to action is what is typically called as a policy. So when I take an action, I end up to my next state. If my next state ends up being close to my goal state, then I know a robot has done a good action, so I give it a high reward. So the whole game is to come up with a sequence of actions which can maximize the reward that the agent or the robot is getting. Right? But let's think about how we initialize this problem. Right? Initially, we don't know anything about how to manipulate the rope. Right? We start off with the parameters theta being random. What that means is that initially, the robot is taking a bunch of random actions. Right? It is acting randomly. So now how likely is it that by doing a bunch of random actions, I'm going to go from this image to actually going and tying a knot? Like, how likely is it? And it's very unlikely that I'm going to tie a knot. So if I never tie a knot, I would never get a reward. If I never get a reward, that means there'll be no learning signal which will be there, and my policy will essentially remain random. Right? So now, this is exactly why these kind of things work in games, because you can just wait for a long amount of time, just trying a bunch of random things, and hope that once in a while I'm going to strike the jackpot, which is the reward. Right? The other thing to notice is that in these games, I have access to this thing called as a reward, because someone just tells me what the reward is, which I can read from the game. But if I'm operating in a real scenario, I now need to figure out if I am in this state, is this a state of the knot or not? Right? So in the real world, no one is giving me these rewards. So I have to construct my own mechanisms to get these rewards. Now, how do we construct such mechanisms? Like one way to do it is to rely on computer vision to self-build a classifier which can distinguish whether this state is my goal state or not. But then how do we build these classifiers? We leverage a human farm, right? We need to annotate data to build this classifier. And now if I change my task, I need to build yet another classifier. And if I change my task again, I need yet one other classifier. Right? So it seems like reinforcement learning, as we know of today, requires lots and lots of data. It ends up being very specific to the task. And it's unclear where do rewards come from. So how can we go and address these problems which are inherent in this framework? So to motivate this, let's take this example. Right? So what I'm going to tell you is this is a game screen. Okay? And then here is like a blob which is bouncing around. It goes left, right, it jumps around, and once in a while it seems to disappear from the screen, and then it again comes back. Right? So what is happening in these games? Or what is this agent trying to do over here? Right? Anyone? What? It's maybe trying to drive up, right? But in general, it's very hard to say what is this agent trying to do in this scenario. But what if I told you this is simply a re-rendering of this? Right? Now, when you look at this, you suddenly realize what the agent needs to do. It probably is trying to go to the key and then go to the door and maybe skip over these enemies. Right? So we as humans bring in this prior knowledge that we have about the world to be able to go and solve these games. Right? So maybe if we can build in this kind of prior knowledge into our agents can also end up being much more efficient at solving these new tasks that they are given. Right? So now what you can do is what I'm saying you can also quantify. For example, you can have humans play this game. They can solve it very quickly. You give them this game. They take a lot of time to solve this game. Right? And then people also send you angry emails complaining that you're an evil person making them play this game. Right? So, okay. So now we can do the same experiment on my RL agents, right? So I can have an RL agent play this game and this game, right? Which is like a similar thing that we saw before, right? So if you see humans, there's a difference in performance. For an RL agent, there is no difference, right? And the reason there is no difference is because the same thing we discussed before, that they have no way to distinguish between this game version and this game version. So they have no priors that they are beginning with. So, okay, let's see how we can go and equip these agents with priors. The first thing you can say is, let's enlist what these priors could be, and then maybe we can go on and build it in. Right? So, for example, you can assume that one prior is that I make use of the game semantics, that I know this is an enemy, this is the key, and the key goes inside the door. Now, to study how important is that prior, I can come up with a version of the game where I change these blobs so that when you look at these blobs, they communicate no information about the semantics. Right? Then I can have a human play both these games, the original one and this one, and that will help me quantify how important is the knowledge of semantics in this environment. Right? Similarly, but even if you play this game, you are naturally attracted to these blobs which are there. You don't go in free space, free black space, and interact over there. So you have one more prior which is built in that you want to interact with objects naturally. Right? So you can, again, go back and study this. For example, what you can do is construct these artificial object blobs, which are kind of like placebos. So there's not a real object over there. But so you hide the fact that there are objects in the world. And you can, again, compare the performance between this version and the original version to figure out how important objects might be. So similarly, you can run like a bunch of studies to figure out what are these priors that we can have, and we can try to hand design these priors. Right? But if you look at hand designing, even if I consider the question of what is an object, so some of you might say that tree is an object, but I might as well say a branch is an object. I might also say a leaf is an object. Right? It really depends on what I'm trying to do. For example, if I'm driving in a car, I don't really care about the leaves and the branches. The whole tree is an object which I want to avoid. Right? Whereas if I'm drawing something, I care about all the details, and each leaf and each branch is an object. Right? So even these notions which seem very intuitive to us, concepts such as an object, they end up being very hard to computationally define and actually encode into our models. Right? So while I think there is a lot of research happening in this direction, which I think is truly exciting, in this talk, I think I'm going to talk about something different. How can we learn these priors from experience? I mean, can I play a lot of games, or can I interact with in my environment and try to learn this kind of prior information to solve new tasks that are given to me? Right? So let's delve a little bit into more detail to see how we can do this. Right? So one example that we know can learn from experience are babies. So over here, you can see this kid is just playing with this toy, just keeps hitting this object for a long time. Right? That's all it does for not just like in hours, but days at stretch. Right? So what might this kid be doing? For a long time, people said, oh, well, this kid is doing a bunch of random actions. We don't know what it's doing. It's just randomly playing with these toys. But there's a lot of work which has happened in psychology which suggests that what these kids are doing are actually conducting experiments. When the kid is throwing an object, putting it into its mouth, it's trying to understand that if I apply these forces, how do these forces affect the objects in my surroundings? Right? In a way, the scientist or the child is like a scientist in a crib, which is trying to understand what is happening in his world. So maybe we can take this inspiration of how children are learning about their world by experimenting to have these robotic agents which can also conduct experiments in their world and learn from these experiments some useful information which they can use to solve new tasks. So now if we want to take this paradigm seriously, the first question we need to answer is, what are the experiments that the agent is going to run? Right? And then when it runs experiments, it's going to collect data. Right? Then the next question is, what are you going to do with this data? What kind of models are we going to define once we end up getting this data? Right? And once we have these models will tell us what to explore next or what kind of experiments to run so I can refine my models. And I want these models to be able to solve new problems, learn from a few examples, and require minimal supervision and hopefully just work from the sensors that I am putting. Right? Now, these models and exploration kind of creates this never-ending loop in a way. So my mechanism for experimentation tells me what kind of data I want to collect, which I use to update the model, and then wherever my model is inaccurate, it tells me what experiments to run. So we look in slightly more detail into how to construct this. Right? But if you let this agent just explore in the world, there's going to be too much to explore. Right? For example, I might just start counting how many tiles are there on the floor, or I might start counting how many lights are in this room. But we don't care about a lot of these things. What we want to do is to somehow bias our agents to explore useful things. Right? Sometimes what is useful to explore could be obtained by just observing what other people around you are doing, or sometimes getting a reward from the environment saying these are the tasks which might be useful. And if we talk about any learning system, it's important to specify where are we starting from or what is the initial state. So let's start with one of these questions, which is how do we learn models of how things work? So to do this, we had a robotic agent, just like children are playing with toys. We let this robot also play with some toys that we gave it. Right? For example, over here, you see a table, and the table has one object. It also has a couple of objects, 1 to 5 objects at any point, and the robot just keeps on pushing this object for a long period of time. Right? And what the robot is trying to do is, by this notion of pushing, trying to understand something about the physics of pushing. So one way you can solve the problem is to say, I know physics. Can I use physics to solve the problem? Other way is that just by interacting with these objects, can I learn about the physics of interaction? So now what is happening is I see an image, I run an experiment, which is an action that I take, And when I run this experiment, I get my new image. And from these images and my actions, I want to learn some kind of a model. So now, one kind of a model which I could learn is saying that if I have my image and my action, I want to predict what is going to happen in the future, because if I can make an accurate prediction, then I understand something about the world. But then the question comes is, what should I be predicting? Right? One thing I can predict is I can try to predict this new observation in pixel by pixel, right? I can predict every pixel of the new observation that I get, right? And there's a lot of work trying to build such models, which are typically called as like forward models in pixel space, right? But is this the right thing to be doing, right? I mean, for example, just imagine that I give you this glass bottle, and then I drop this glass bottle. Like, do I really want to predict where each and every piece of glass goes? Or do I really want to predict where all these molecules of water go? Probably not. Probably what I have is an understanding that if I drop the bottle is going to break down, and maybe I should not step on these pieces of glass, right? This is the kind of understanding I want, but unfortunately, I don't have supervision for that. Right? All I have is this data in which this bottle is breaking down. Right? So the question is, in what feature space should I actually build this model? Right? Obviously, I don't want to build this in the raw pixel space. Right? So if we look at it, right? I mean, so I have this image which I'm seeing. I have some neural network which I have. One model which I could build is take the image, process it to get some features, get my action, and try to reconstruct the image. Right? Now, instead of building these models, we can also build different kinds of models. For example, I can take these images and then just predict the action that I took. Right? So given the current image I see and the image after an action, what is the action I'm taking? Right? This model is what I'll call the inverse model. Right? And it turns out that if you train both the forward model and the inverse model together, you can kind of bypass this question of predicting in the pixel space. And I'm not going to go into a lot of details of how that is happening, but if you have any specific questions, I'll be happy to take them after the talk. What I'm going to show you is if the model actually works or not. Right? So what we're going to do is we're going to learn both the inverse model and the forward model together in the hope that we can bypass the fundamental problem of prediction, which is I don't want to predict each and every pixel of a future observation. So we just didn't have a robot perform one experiment of pushing these objects, but we can have robot do a bunch of different tasks. Right? For example, over here, the robot is now playing with a rope. Right? So it picks up the rope and keeps the rope and keeps doing it for a long period of time. And in the other case, you see here's like a small robot just moving around in an office environment. Again, it takes actions, and it might bump into some things to realize it has bumped into some things, or figure out where it can actually move. So now the question is, if we have done all of these experiments and learned these models, how good are these models? So the way we could test this model is, I can have the world in the current state, and I can give an image of the world in a different configuration. Right? And we can test these models when I give new objects, which the robot might not have seen before, or objects which might be of different geometries and so on. So over here, you will see that the robot can configure this one or two objects that I am showing over here, although the robot has never seen before. So in this case, you might think, well, these are some objects over there. All I need to do is to push. So I learned from a lot of data, and maybe I learned something about pushing. But the cool thing is you can take the same framework, and now I can go to, say, locomotion over here, right? Or not locomotion, but just navigation over here. So I am in this new environment, right? And I've never seen this new environment ever before. I give you an image that you're seeing, and then I give you a goal image, right? Which is where I want you to go to. Now, what would you intuitively do? Right? You don't have the map. You just see one image, and there's no other information that you have. And so how would we solve this problem? What? You what? You look around, right? So you would try to look around to solve it, right? Let's see what our system ends up doing. It actually learns this behavior of looking around to go to the goal image, right? But the thing while you can solve this problem with techniques which are there in robotics today, but over here we didn't have to tell the agent it has to look around. It discovers on its own this behavior of looking around to go to the goal image, right? Similarly over here, if I again show a current image and a goal image, the agent kind of learns that it needs to follow a particular trajectory to go to the goal image, right? And the success on this is, it's like around 80-85%. So it's not always successful, but it's successful most of the times over here, right? I can take the same kind of learning algorithm and go to a different problem, which is the problem which I mentioned earlier. I have my current image, which I show in this configuration, and then I show you an image of a knot, right? And then let's see if our agent can actually perform this task. And what you see is that the agent can actually perform this task, right? The accuracy on this task is not 100%, right? What I showed you on this task right now, it's 18%, right? So it's like not 100%, but it's much better than random chance, right? So, okay. Now, what these demos are showing you is that by learning in the world, or by experimenting in the world, I can learn some models which can perform new tasks which my agent has never seen before. But then the performance of 18% is not very good. So what do we do? How can we go and actually improve this? So, okay. So, but if you look at humans, when they're trying to solve these tasks, such as knot tying, a lot of the times they're observing other humans, how do they perform this task, right? So can we get a demonstration of a human doing this task and learn something from that demonstration to help me improve my accuracy? For this problem of learning from demonstrations, or implementation learning is a well-known problem, well-studied problem in robotics. So here is one typical way in which you would give a demonstration, right? So to perform the task, a human would move the robot. It can either move it by actually physically moving the robot, or you might also have your PlayStation controllers or other setups to move the robot. Now what you are getting is, you get the observation which the robot is seeing, and the action which the robot is taking because you are moving the robot. So you have access to both the observations and the actions. And from this, you could learn a model which goes from observations to actions, right? That is how you can replicate what the robot was demonstrated by a human. But this procedure ends up being very tedious because for every task, you now need to give it a demonstration by actually moving the robot. And then you have to do it for every single task, right? There's no notion that if I have done 5 tasks, I can go and do the 6th task, right? So instead of this, what we want to do is for a human just to show a video. And just by the video, can the robot learn something about how to perform the task, right? That means that instead of having access to images and actions, I only want to have access to images, that I only want to observe what the person has done without having the person actually move the robot to do that task. So now if I want to copy what the person is doing, what I essentially have is a sequence of images, right? And if I want to copy it, what I'll need to do is say that given the image that I have and the image I want to go to, what is the action that I produce? So if I can solve this problem, then I can go and copy this demonstration, right? So now this is exactly the inverse model that we were learning from data, which would take 2 images and learns to predict the action which the robot had done, right? So now if I get a sequence of images, I can just recursively apply this model to imitate what the person has shown, right? So now you can do this trick, and now the cool thing is that you can now go to any different configuration of the rope. You don't have to be specific to one task, because if I give you a demonstration, which is a sequence of images, I can use the models that I have learned before to copy these new tasks that have been shown to the robot, right? So for example, over here, one of the students working with me, he demonstrates this video. Now you see like steps, and then the robot can copy this demonstration. Now if the demonstration is actually helping, then the accuracy on the knot tying task should increase, right? And that is what we find, that instead of having 18%, once we end up doing imitation, it ends up improving to 26%, right? So in some ways, yes, we got an improvement, but in some ways, 26% is still low, right? It's not something which we could have deployable systems that we can have, right? So what are more things that we can do? Right? So one thing, if you realize, is once you are learning, you don't always have an access to an expert in the end. Many times you have this process where the expert and the agent interact with each other, right? So instead of bringing the expert just in the end, maybe the expert can give some interesting knowledge which can help you explore better, right? So what do I mean by this is that maybe the expert can come in and say that if you really want to go and tie a knot, maybe you should explore states like this more instead of doing some kind of random exploration. Because if you can explore these states, you are much more likely to tie a knot, right? So it's kind of a very weak supervision you can do to guide someone in a particular direction. So now the question is, can we make use of this information? Right? It turns out that we can make use of such weak supervision, and then a knot tying could improve to around 65%. Right? This is by making use of some of this information, but also improving the quality of the models that we are learning. Right? So what we have seen is that through a sequence of steps, by taking different learning approaches together, right, where you are trying to build a model, you can learn from an expert, but you also have this interactive process of where the expert and the agent learn together, we can actually improve the performance of a system one by one. Right? Now, let's see, how can we maybe go towards improving it even further? Right? So right now what we talked about was that I had a human which told me where to explore. Right? So can I get rid of this assumption and I don't require a human which tells me what to explore? Can I have an agent just explore the world autonomously? Right? So to illustrate how we can build such systems, I'm going to consider this game of Mario over here. So you see the screen, and here's the agent, and you can take 4 actions. Right? And the usual things happens when you take the actions. If you move left, you would move left. You take right, you would move right. You go up, you go up. You press down, nothing more happens. Right? And now, so the kind of models we were trying to build was, given that I see the observation right now, if I do an action, I'm trying to predict what is going to happen next. Right? So now, let's say in this case, if I press up, the prediction is the agent will go up and then it will come down. Now this is exactly what happens in reality, so everything is good, right? I make a prediction and the reality matches what my prediction is. Right? But what about this scenario? Right? My agent is over here. It has never seen an obstacle before. Now if I ask the agent to move right, the prediction is that the agent will go through the pillar. But the reality is it will get stuck because it can't go through the pillar. Right? So there's a mismatch between what you predict and what happens in reality. Right? So there's an error in your prediction. So what if we incentivize the agent to take actions which maximize the prediction error? Right? Then it will lead the agent to come and hit this tower or this tower more often. And once in a while, when the agent goes near the tower, now again, if I predict what's going to happen when I take the up action, the prediction is going to go up and then come down. But in reality, the agent never comes down. Right? It kind of goes on the tower and it climbs it. So again, you end up having this prediction error. So if somehow I can make my agent be curious about actions which lead to prediction errors, it can, for example, over here, learn the skill of coming to the tower and then jump on top of it. Right? So what we'll do is we'll say, I have a model of the world that I'm learning, and then I'm going to take actions which are going to break the model. Right? And by breaking the model, I mean which are going to increase my prediction error. Right? And I'll take this data to go and update my model again. Right? And that way I can keep on learning new things about the world. Right? So we can see what this system ends up doing on this game of Mario. Right? So now what you'll see is this agent, it learns to kill enemies, jump over these pipes, and in general, make progress in the game. But in this scenario, we are giving it no rewards. So there's no rewards. The agent has access to no rewards. It is learning these behaviors just out of its own curiosity to explore more in this environment. Right? And then these behaviors, such as jumping over enemies, pipes, and pits, they're not specific to this environment. Now I can take this agent, and I can just take it and drop it to a new environment over here, which is a different level of the game. And although you have not seen obstacles like this, or you have never seen these ducks over here, the agent can still deal with these new environments that you might be faced with. Now we can take the same system and apply it to this case of indoor navigation, right? And we can do the same test where I train the agent's curiosity on one map, and then you can test how well or what are the kind of skills you learn when you go on a different map, right? So what you find is on the training map, the agent learns the fact that it should not bump into walls, but it should move along corridors. Now, why does the agent learn to move along corridors? Is the fact that if I can go as far as possible for my initial state, that is where it is likely my model is not as good. Because if I go as far as possible, I'm seeing new things which I have not seen before. So that is where my prediction error is actually high. So that will cause the agent to naturally learn to move along corridors instead of getting stuck in some other region, right? And now I can take the agent over here and just drop it in a new map, and then you see it has this exploration behavior of trying to explore this room and then come out. And then, one thing you might think is, well, what happens if there's some stochasticity in the environment? For example, there is a television showing white noise, and my agent is very curious about new things. And if I'm seeing this white noise, then every second I'm seeing something new because there's no way to characterize this white noise. So maybe my agent will just become very curious about seeing this television screen showing white noise because it is giving me new information at every time point. So what we can show is that if we use our formulation, we can kind of skip these parts of the environment which do not affect the agent. So agent can kind of not get curious about these nuisance things in the environment, but only become curious about things it actually cares about. Right? So this is like one way in which I can use my model to actually encourage how to explore new things in my environment. So in a nutshell, I think what we have looked at is a mechanism by which we can run experiments. Right? And these experiments kind of give us data which help us learn newer models about the world. And these models tell us what experiments to run, which gives you this never-ending loop of learning. But as we discussed before, there is too much to explore in the world. And that is where we kind of can learn from other agents. We saw these specific examples on the task of rope manipulation, of how learning or observing other agents can help you improve your accuracy. And I guess and the other question is, what is the initial state? I think in all these works, we assumed that we are building these models. And the specific models we assumed were these forward and inverse models that we are building. And I think how much time do I have? Couple of minutes?
You have 7 more minutes.
7 more minutes. Okay.
So Evie can use a couple of minutes for questions.
Okay. So, I can either stop here. I'll just ask the audience. I can either stop here, or I can tell you a couple of, other things which might be, slightly related and slightly different. What do you guys want? Questions or more content? How many of you want more content? How many of you want more questions? Okay, no questions. Perfect. So either I did a tremendous job explaining everything, or I did a very bad job. Okay, so let's look at slightly more content, and then maybe we'll stop a couple of minutes before to take more questions. Right? Okay, so we were talking about this, building this agent which can keep on learning new things, but when you learn new things, and if you have finite memory, you'll also forget about older things. Right? Now, this is a well-known problem in machine learning. I'll try to illustrate you what the problem is. Right, so I have some data which is, say, x, and I'm trying to learn a mapping from x to y. Right? So I have this model which I have learned, which is my function f, which predicts y given x. And say w are the weights of my neural network. Right? Now, in the future, it is daytime now, I get to nighttime. It is night, now images look very different. In the nighttime, my data is slightly different. I want to predict maybe something different. I want to say headlights are on or off. Right now, I have my weights W2, which I get by tuning my initial weight to perform the next task in a slightly different environment. Now, this is what my neural network looks like at this time. Right? Now, what about the performance on the first task? Right? Now, if I apply the second model, which I've learned over time, on the first task, what do you expect to happen? What? Worse, right? Whereas as a human, if I see something in the daytime, then nighttime, when I wake up again, I do completely fine, right? I do not forget about what I learned in the daytime after being exposed to data in the nighttime. But turns out in machine learning, that doesn't happen. And this problem is called as catastrophic forgetting, that you forget about things that you learned in the past, especially when you're getting data sequentially. Now, what is the fix that we have in machine learning is we assume we have access to all the data together. So we can assume all the data is identically independent, or it's randomly is independent, and then we put all the data together. But in the real world, we never have access to all the data together, but we only can get it one after another, right? So for example, I can take a network and train it on this CIFAR data set, which is just an image classification data set, right? And it has like 10 classes like dogs and frogs and whatever, right? I mean, there are 10 classes in this data set. And then I can have a second task, which is say some other set of 10 classes, right, which could be my second task. Now, if I train on first task, as I give new tasks, the performance on the first task actually goes down. What you see is I can get good performance on task 1, but after training on task 2, the performance on task 1 is actually degrading, right? This is something that we don't want to happen, right? So now we are trying to work on methods which can address this problem of forgetting, which is happening, right? And one of the ideas, okay, what is the simplest thing you can do? The simplest thing you can do is, well, let's store one network for every task, That would solve the problem, but then, it's not scalable because then you need a new network for doing everything, and then you cannot share information across networks, right? So, I mean, one of the ideas we're exploring is that what we can use is the principle of superposition, right? Where we can store all models which might be different, but in superposition with each other in one network. So you can think of this as having some dictionary of models, and you can compose these dictionary of models as you want to solve new tasks, right? And okay, I mean, as the results will show, this can prevent this overfitting from happening. Now again, this is just like a small preview into this. Again, if you have more questions, feel free to ask later. Right? Then I think we are interested in making RL approaches be more sample efficient. I mean, one thing we talked about was how you can collect this experience and so on. Other is we can also innovate fundamentally on the architectures to make approaches more efficient. Right? So over here, for example, you'll see this robot, again, trained in simulation, trying to stack these blocks. And what we can do is we can learn these kind of stacking tasks, which can stack these 6 or 7 towers. And then we can take the policy that we have learned and try to generalize to new things. For example, over here is a tower of length 7 instead of training on 6. Or you can do like other configurations, right? I mean, you can configure blocks as you want and have the agent actually perform that. And then also kind of exploring things in a more complex manipulation setting where you might have a human-like hand trying to manipulate objects, and you have inputs just not from vision, but also from touch sensors on your hand, which might be there.